So the destructor would be, I will call delete node and root. So the root will be deleted. I won't write the delete. The destructor will let's forget about the delete node right now. Start with the add a string. So void a tries colon add string. Okay, and string is the value. So now I have to add a string in this thing. So what I will do is, let's say T E A exist, and now I want to add T E D. Okay. So what I will do is I will take a node A tries node star current, and I will point it to the root. So that current will start pointing to the root. And let's say E, A, T exist and stuff. Okay. Then what I will do is, for integer I is equal to 0, not a very good implementation. It can be not a very efficient implementation. This can be improved. You can take like a binary trees or something, hash table for all the nodes and stuff, but I'm just taking a simple list, which is not efficient. But I'm just implementing a simple one. So I is less than 0, I is less than sg value dot size. So basically the size of this string, which is TED, and I plus plus. Okay. And then I will say A tries node star child is equal to find node current comma sg value dot add I. So basically what I am doing is I am saying that current node is 0, and I am saying that for I is equal to 0, so 0th one, find a children which has the value t. If it returns me something, then if it does not return me something, I have to add a new value. So I'll say if child is equal to null, which means that I did not find the value. Let's say I wanted to add food, eat food, right? So for root, f did not exist, so I would have to create a new one, f. And there is a bug in this one that like the lowercase and uppercase is
same.
No, it's different.
I mean, it is treating same.
No, but if I add a t in this, it will create a new node. So, but in interview you can point it out to the, and then you can.
So how it is bug?
No, this is like this is what he's saying. Like if you add the capital T and then again if you have another word which starts with a small t, EEA, so it will know the capital T and add one small t.
So it's based on our coding. We can make it perfect, right?
This is what he's saying.
Yeah, I'm just saying this is a simple implementation. Yeah. So let's say the child is equal to null. I did not find f. Then in that case, what I will do is I will create a new node. Child is equal to new a tries node, and then child arrow c value is equal to sc value add I, and we will check if this is the last value, if this is the last one. So we'll check if I is equal to SE value dot size minus 1, which means that if this is the last character,
Right.
if this is the last character, then we will say child arrow
Child dot
is end
is and equal to true.
character is equal to true, else child arrow is end character is equal to false. Okay. So if f did not exist, I will create a new node and I will find out if this is the last character. If this is not the last character, I'll set that this is not the last character. If it is, I'll add it. Okay. So that was the condition when I did not find the child. If I did find the child, then what I will do is current is equal to child. So let's say it was TED. So first time I was at current, I searched for, I did a find T, it found T. Then I will say current is equal to this thing. Then I will say child is equal to find node current and SGR. So it will find, now it will try to find E. It did not find E, so it will create a new node E and check if this is the last one. No. Then it will say that, oh, this is not the last word. Then it will find D. This does not contain anything, so it will, oh no, DE is there. Sorry. So it finds E and the child was not null, so current becomes equal to E, and then after that it comes back, it does not find D, so it will create a new node D. Yeah? Yes, simple, easy. Yes sir? Yeah?
Yeah, सही है.
Okay. So this is very, very simple implementation. All you need to do is, if you want to convert it into C#, what you need to do is just remove this, and there should be SC value I, or like you have to convert it into character array and stuff, and do the I, and this will be I, and this will be len.
All the arrow will be changed to the
Arrow will be changed to dots. That's all. That's all you need to do.
Yeah.
So you need to add it to the vector, right? To the array.
Uh,
The child.
The child I. Oh yes, yes. So and if this not, yes, thank you for pointing out. So if this does not exist, then what I will do is I will say current arrow children dot push back. So for array strings it will be current arrow like children dot push or child. So you need to push the child in that thing, in its list of things. Okay. So easy. Like, did you guys understand? Yes.
Just 1 second.
Okay. Yes. So next I will write a function called find node. So a tries node star a tries colon find node, and a tries node star child comma character C. This is just a simple function which whatever I can should name this current. So I want to find if the current node has a children which has a character C. All I need to do is go through all my children and check their C value. If that C value is equal to character C, I will return that character, otherwise I will return null. So that is very easy for integer I is equal to 0. I is less than current arrow children dot size I plus plus, and we will check a tries node star node is equal to current arrow children.
What is that children current arrow children dot size?
Size of the array list. So how many children do I have?
Okay.
So current I'm a node. I'm a node. I will try to find how many children I have. So I have to go through that loop, and then I will say that okay, the children at 0, what is their value? So where was that? Yeah.
You say
At I,
Find out, right?
at I, and then I will check if node arrow C value is equal to C, we'll return node, and if it comes out of this loop, we'll return false, null. Okay? Yes. Yes.
Only one character we are checking, right?
We are checking one character. We are checking one character at a time. Right? And this function was getting called by search word or add word. Add word. This function will also be called in the search word. Do you want me to write the search word? I can just.
You can call it every time, right?
All I need to do is.
For a word loop, you will be calling
Yes.
it every time.
Yeah. So for a word, if I have to find Ted, I will first call E with the root, and then E, and then if I find it, then I'll say
Yeah, current equal to
current
child.
is equal to
Child.
a child at whatever.
Yeah.
Yeah. Do you want me to write the code for that? Simple. Yes. No.
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 Only thing is, only addition thing is, I think you need to check in there, means like if it's last end is
Yeah.
true or false. Right?
Yeah.
If you reset that after.
Okay.
So in interviews they ask like what is try, explain.
They will ask you a phone book or something and say that okay, this is what it is. Then you can say okay, I can implement it using a try, and then they'll say, do you want to implement using? How do you implement a try? And then you explain the structure, and then you'll say, I will implement it like this. Okay. Okay. So that was tries. There's another thing which is called suffix tree, and he did a question: find the longest longest common substring or something. That question, those kind of questions can be solved by the suffix tree.
And
And
it's common palindrome as well.
maybe yes, I haven't given a thought to it. But basically, in human genome sequencing and stuff like that, there is like the DNA sequence. So you'll say that okay, bacteria A has a sequence of A, B, 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 A, B, 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 A, C, and bacteria C has a sequence, let's say B, B, A, right? And then A, C, D, D, B. So let's say this is the sequence. So you'll say, oh, these two are matching, and then you'll say, okay, this is matching. So you can actually figure out that, okay, this is, I'm just giving a small example, but the DNA sequence is a big thing. Once you start matching them, then you'll figure out that, oh, it matches over here, it matches over here, it matches over here. And then you can figure out, okay, it is matching at these places, so, and this is missing, so which means you can actually figure out how the bacteria evolved from bacteria A to bacteria B and stuff like that. So those kind of calculation. But the thing is, like, if you start matching these things, it will be really difficult because the number of computations will become really huge. Because if we do ACD, you have to go ACD the entire thing. You don't know where it is matching, right? So for solving those kind of problems, suffix tree is actually better. It actually takes a really long time to, a really long space, and we will see how we can actually do the optimization of the space. And but you will see that it actually
Very fast.
it is fast. Okay. Let's say, so what we will do is, there will be one big substring, a big string, which will be there, and there will be second string, and you will try to do operations on the first string. So let's say there is a string called T.
Banana.
Not banana. Banana is confusing. I did banana. It is confusing.
Yeah.
So let's not do banana. Let's do T. Okay. T is, let's say, ABA, ABA. Okay. Let's say this is the sequence. Okay. So what is a suffix tree? Suffix tree is basically, we want to find all the sequences of this, all the suffix of this. Right. So let's do one thing. Let's add a dollar to it. So T dollar would be ABA, ABA dollar. And you will see how dollar actually helps us find the substring. Okay. Let's bear with me for a second. We just added a dollar at the end. Now we'll start finding the substrings. So substrings of this is, one is dollar. Let's start from the end. One is dollar. Second is A dollar. Third is BA dollar. Fourth is ABA dollar. Right? Fifth is AABA dollar.
BA dollar.
Dollar.
And
ABA dollar. We all agree that, we understand that